Okay, everybody, welcome back. We don't have a microphone today, so I'll just try to speak loudly. We are continuing on with our discussion of substitution and elimination chemistry. The key issue last time was you seeing that the SN2 and the E2 reactions compete with each other because the LUMO of an alkyl halide is both on the alpha carbon and on the beta protons. So I thought it would be good to sort of contrast both reactions, see where they differ, and see what considerations can help you decide whether a reaction should go one way, the SN2 way, the other way, the E2 way, or perhaps lead to a mixture of products. And I'm going to show you a situation which will lead to a mixture of products. So to begin with, let's remember that the SN2 reaction rate depends on some rate constant, depends on the concentration of the nucleophile and the concentration of the alkyl halide. And we could say the same actually is also true for the E2 reaction, that the rate of E2 also depends on some rate constant, concentration of the nucleophile. And actually, I'm going to broaden out the term nucleophile here because we're going to see that in the E2 reaction, our nucleophile actually is acting as a Bronsted base to remove a proton from the beta carbon. So we'll just be general and say that the SN2 reaction depends on the concentration of nucleophile / base. For our purposes, a nucleophile is a Lewis base. A base is a Bronsted base that removes a proton. A Bronsted base that removes a proton is a nucleophile, is a Lewis base. So we're going to use those two terms in a related way. Understand, though, that for our purposes, a nucleophile is going to attack carbon. A base is going to attack a proton. In any case, if we draw this chiral alkyl halide starting material, this chiral alkyl bromide, and then we use ethoxide as our nucleophile. Normally you wouldn't buy this as just ethoxide, you would need to buy it in a bottle with a counter ion. So the counter ion there is sodium, and for our purposes the counter ion isn't going to be important other than it's there and spectating. I write it there for completeness. The SN2 reaction, we would show the lone pairs on the nucleophile attacking the alpha carbon, attacking the LUMO at the alpha carbon, dumping electron density into the sigma star, leaving group leaving, and then giving you this product. Backside attack gives you inversion of configuration. You must show that or you do not understand what the SN2 reaction is. Okay, the key mechanistic issue here is backside attack leads to inversion of configuration. Now, the same molecule, ethoxide, the negatively charged oxygen, is not only a nucleophile, but it's also a decent base. You can tell it's a decent base because its conjugate acid, ethanol, has a pretty high pKa of around 16. A little bit later today, we will talk about what makes a good nucleophile good and what makes a good base good. In any case, except for now, that ethoxide is both a good nucleophile, meaning it is good at attacking carbon, and it's a good base, meaning it's good at attacking a beta proton. So we can take the exact same starting material and expect an elimination reaction to occur. Now, in an elimination reaction, the nucleophile / base is going to remove a beta proton. So it's good to look and see the beta protons that we have adjacent to this alpha carbon. So here's the alpha carbon, and here's beta proton 1. And then we'll use a different color for beta carbon 2, sorry. So the carbon that's adjacent to the alpha carbon we're going to call a beta carbon, and then the protons on that beta carbon we're going to call beta protons. there are 3 beta protons on beta carbon 2, and they're all identical. You can see by rotation around the bond between beta carbon 2 and the alpha carbon that each of those protons can interchange where it is. So we're not going to worry about the fact that there's 3. There's not going to be 3 different products if our nucleophile attacks the purple beta protons, just 1. However, on beta carbon 1, you do have 2 distinct protons. And it may not immediately be apparent that they are distinct. So what we're going to do is draw the products that come from removal of each of them. Okay? So, but first, let's simply draw the product that comes from removal of one of the purple beta protons, the one on beta carbon 2. To show that, copy this, we would simply show the nucleophile attacking one of these protons. Now remember, the key mechanistic stereochemical requirement of the E2 reaction is that the beta proton must be anti to the leaving group. Because all of those 3 beta protons are identical to each other, and because I have free rotation around this bond between alpha and carbon and beta carbon 2, it's going to be possible for one of these beta protons to rotate and become anti to the leaving group. And which one it is inconsequential, because either way, you'll get the same product. So I'm not going to worry about redrawing this molecule such that one of the purple beta protons is anti to the leaving group, because it's not going to make a difference. So I'm going to draw in purple the product that we get from that elimination reaction. All right. So that's one of the alkene products that we can get from the elimination reaction. And again, what I was saying is it's inconsequential which of these protons is actually anti to the leaving group, because in the product, you can't tell which one it was. What's left behind, 1 proton gets removed, 2 are left behind. They're the same thing. You really can't tell. All right? You with me so far on that being a product? Okay. Here's where it gets tricky, and you're going to need your 3D visualization skills. So let's redraw the molecule. As I've drawn it, on the blue beta proton, which of those 2 is anti to the leaving group? HB, okay? So that's the one that's going to get removed in this particular conformation of the molecule. So I'm going to show ethoxide removing HB. As that happens, electrons will kick down, form a new pi bond between alpha and beta 1, and then the leaving group leaves. Now, what we're doing now is similar to the example I did in class towards the end of class last time. The stereochemical relationship between groups in this conformation as the reaction proceeds has to stay the same. So notice that as we're removing HB and forming a new pi bond here, and the leaving group is leaving, we're going to be forming an alkene here between alpha and beta 1, and we're going to need to decide what isomer, what stereoisomer we get, because the alkene is going to have a group on this side and a group on that side. So we're going to have the opportunity to get cis or trans. Now, the fact that I'm removing this beta proton HB that's anti to the leaving group, and in that conformation, the methyl group here is anti to the methyl group here, that spatial relationship isn't going to change as the reaction proceeds. So as I remove HB, the product I'm going to get is this one, where the methyl groups that were anti to each other in the reactive conformation of this molecule will still be anti to each other in the product. Do you see that? If that's confusing, what I want you to do is go back and draw a Newman projection looking down the bond between alpha and beta 1. Convince yourself that not only that when HB is anti to the BR group, that this methyl group is anti to this one. And that relationship stays the same as we form the new bond. So this removal, what I'm telling you is removal of HB leads to the transalkene and only the transalkene. Now what about HA? Is there a possibility that we can rotate around the bond between alpha and beta 1 such that HA could be anti to the bromo leaving group instead of HB? What would that look like? Let's imagine that. Let's erase those three substituents. We're going to keep beta 2, alpha, and beta 1 all in the plane of the page, but we're going to rotate around the bond between alpha and beta 1 such that HA, which was pointing out at us, we're going to take a hold of HA and rotate it, tipping it down into the page and below the page. Okay? So that should put HA here. Where should HB be located? HB used to be down. I'm going to rotate it up and into the plane of the page. HB should be here, and that would put the methyl group here. All right? Have we done that correctly? If you're struggling to see it in your head, that only means you need to work with the model set. You need to build this model, do what I said, rotate HB until it's anti to the leaving group, and then redraw the molecule and see how that changes. Okay? This is important. If you're not good at it, take the time to get good at it. It's going to save you some points on the exam. All right. Now, notice, and I'm not drawing the Newman projection, but notice now that HA is anti to the leaving group, notice the relationship, the new relationship between the methyl group of beta carbon 2 and this other methyl group. What's their relationship? They're not anti now, they're what? They're gauche to each other. They're sort of on the same side of the molecule. What that means is when the base comes in and removes HA, and we form the new pi bond and the leaving group leaves, those two methyl groups which were on the same side of the molecule have to still be on the same side of the molecule. And so now the product we get from removal of HA is the cis stereoisomer. Okay, so there are three possible elimination products. If we remove a proton from beta carbon 2, we get the what I'm going to call the terminal alkene, or the monosubstituted alkene, where only one of the four groups attached to the double bond is not hydrogen. If we remove protons from beta carbon 1, we get disubstituted alkenes, that is, alkenes where two of the four things attached to the double bond are not hydrogen. But if we remove HB, we get the E, or trans stereoisomer. If we remove HA, we get the Z, or cis stereoisomer. This is incidentally how you tell that HA and HB were different to begin with. They have to be different because you remove them and they lead to different products. That's an observation that's going to come back to you maybe if you take the OChem Lab 353. We have a word for these two protons, HA and HB, that lead to two different diastereomeric products. These are two cis and trans diastereomers. The word we're going to use for HA and HB is that they are diastereotopic. That's not going to be important for right now, but you do need to be able to see that HA and HB are not equal. And the word that I'm just previewing for you that you will use for protons like this probably in the 353 OChem lab is that they are diastereotopic protons. Yeah?
So are the H's on the left, the purple ones, are those all on the plane of the page?
Are those all on the plane of the page? No, I did not show dashes and wedges there simply because they're all the same, and so so it doesn't matter. But yes, that should be an sp3 hybridized carbon. You could use dashes or wedges there, and that would be fine. Yeah?
Are the diastereomers equally stable?
Ah, good question. Are the diastereomers equally stable? No. Diastereomers don't have to be. But in this case, no, those two alkenes are not equally stable. The cis alkene has steric issues because the two CH3s are now constrained to be in the same plane. If you built a model, you would see that those protons are knocking into each other a little bit.
So would the trans be the only considered the major product?
The trans would be more stable, for sure. The cis would be less stable. And you would expect, so this is an interesting question then. If you have multiple alkene products and they differ in stability, which one should be the major one? Now, if you read in the text, there is a rule for that, and there's a reason behind the rule which we can talk about. The rule from the text is named after a dead chemist. Depending on how you like to transliterate Russian names into English, it's sometimes written in those couple of different ways. But it's the Zaitsev rule, which says that in elimination reactions, the most stable alkene is the major product. Now, you're going to see there's two different types of elimination reactions with two different sort of reaction coordinate energy diagrams. The Zaitsev rule holds for both types of elimination reactions, but for different reasons. It will be enough if you want to just memorize that the most stable alkene is the major product, though there is a reason why. We've talked about cis and trans isomers and why the trans isomer is more stable than the cis isomer because of steric issues. Another thing we need to talk about here is what's the relative stability of the monosubstituted alkene versus the disubstituted alkenes. And the answer is, as we've talked about, most stable alkene being the major product, more substituted alkenes are more stable. What do I mean by substituted? I understand that we're throwing that word substitution, substituted around like crazy. In this context, when I talk about a substituted alkene, I'm talking about how many of the four groups on the alkene have I replaced hydrogen with something else. So this is a monosubstituted alkene. Because one of the four things is non-hydrogen. And these are both disubstituted alkenes. Of course, you could have tri- and tetrasubstituted alkenes as well. But in general, the more substituted alkenes are more stable, and then trans disubstituted alkenes are more stable than cis disubstituted alkenes. Okay, the reason for this first rule, more substituted alkenes are more stable, has to do with hyperconjugation. I'm happy to talk about that, but and we may come back to it, but for now I think it's fine to just use the rule, the more substituted alkene is more stable. I actually hate doing that because when there is an explanation, I like to know it. But there's probably more important things we need to talk about. So just put a pin in that, and if we get back to it, we can talk more about it. Fine, I will just say it has to do with sigma. I can't resist. It has to do with on the groups that are attached to the alkene, there are adjacent carbon-hydrogen sigma bonds that can donate into the pi star of the alkene. Sigma to pi star hyperconjugation, that allows for electron delocalization, and it's always stabilizing. The more non-hydrogen things you have attached to the two carbons of the alkene, the more these adjacent carbon-hydrogen sigma bonds can donate into the pi star and stabilize the molecule. That's the short explanation. We can talk about it in more detail later, but that's the reason that more substituted alkenes are more stable. So to summarize, looking at what we've got here as potential products, we have two disubstituted alkenes and we have one monosubstituted alkene. I would just expect you to be able to say that the trans disubstituted alkene is likely the major product. I would not expect you to predict ratios, nor would I expect you to predict that, well, maybe the cis disubstituted alkene should be formed a little bit more than the mono-substituted alkene. I just want you to pick out the major product, which is the most stable one, all right? And if you wanted to know what ratio of products to expect, you would just do what chemists always do, which is go into the lab and figure it out, okay? All right, so those are two sort of summaries of the E2 and SN2 reactions and what you can expect as potential products. Ultimately, I would have, if I had given you just as a problem this starting material and this nucleophile, at the end, I'm going to expect you to be able to tell me that you should see both substitution and elimination products for this reaction. We're not there yet, but we will be soon. And I would have expected you to be able to draw all three of these elimination products and tell me which one's the major one. I would not have expected you to tell me whether the substitution product or the elimination products dominated relative to each other, only that you would expect to see both of them. Hand, yeah.
Just going back a little bit, could you remind me why the first one was monosubstituted?
Why is the first one mono-substituted? Okay, so this ethylene with C2H4, has 4 hydrogens attached to the 2 carbons A and B of the double bond. That's unsubstituted. You replace one of those hydrogens with something that's not hydrogen, that is a monosubstituted alkene. 2 disubstituted, 3 trisubstituted, 4 tetrasubstituted. Yeah. All right, others? Yeah.
Are there any exceptions to the state set rule?
Are there exceptions? Oh, sure, there's always exceptions. None that I think we need to, none that come off the top of my head. So yeah. Good. Now, I told you that the rates of these reactions depend on the structure of the alkyl halide and the structure of the nucleophile. And last time, towards the very end of class, you maybe missed it, I talked about how the structure of the alkyl halide can give you a clue as to whether a reaction is SN2 or E2 or both. And I'll just repeat that here. So we have basically 4 different kinds of situations where we have a halide leaving group, or a leaving group really of any kind. A methyl leaving group, a primary leaving group, a secondary leaving group, and a tertiary leaving group. And if you want to see what I'm talking about, that would be like this: primary, secondary, tertiary. And we said that the rate of SN2 is fast for primary alkyl halides, wicked fast for methyl halides, not as fast for secondary alkyl halides, maybe slower, and too slow to observe for tertiary alkyl halides. And the reason it's too slow to observe for tertiary alkyl halides, we're just going to say no SN2. The reason it's too slow to observe is that these large, or rather the three alkyl groups on a tertiary alkyl halide completely block the sigma star on the alpha carbon. All right? We can show you that briefly in Spartan. If I draw, let's see, I just need to add another methyl group and come here, download it. Molecule not in database. Well, fine. That means we're not going to be able to see the sigma star, but you're going to have to imagine it. The sigma star should be projecting 180 degrees opposite the carbon bromide bond. Whoops, dropped the pencil. Now I'm going to show you the space filling model. And you can see that that little sort of triangle there is the only portion of the alpha carbon that's even accessible, not very much at all. So what we're saying is these groups, these three methyl groups attached to my alpha carbon, the three beta carbons, totally block the alpha carbon so that a nucleophile can't actually attack the alpha carbon. Now notice the beta protons are still accessible, and some of the LUMO is out on those beta protons. So we're going to find that elimination reactions are just fine for tertiary alkyl halides. So let's see. What are we going to do? I'm kind of running out of space. Maybe I'll drag this down. I kind of wanted it to all be on the same page, but whatever. All right, let's write rate of E2 here. It turns out the rate of E2 is very fast for tertiary alkyl halides. And there's a couple of reasons for that. Reason one is tertiary alkyl halides easy for me to say, just statistically have more beta protons to attack. We can go back to Spartan and you can see that there are a lot of beta protons there poised, held anti to the leaving group and ready for attack. So there's a statistical issue that makes the E2 reaction fast. There's simply more beta protons available to attack. And second, hopefully you can see that the elimination product that I might get from a tertiary alkyl halide would be more substituted than the elimination product I would get from a secondary alkyl halide, which would be more substituted than the elimination product I would get from a primary alkyl halide. And so on a tertiary alkyl halide, I have the option to form more stable, more substituted alkene products. Now, some of you should be skeptical about that because the issue of product stability is a thermodynamic issue. Product stability is all about how stable a product is relative to the starting material. But in terms of speed of reaction, we're talking about kinetics, which is all about how high up the transition state is relative to the starting material. And those two things, kinetics and thermodynamics, aren't always coupled. It just so happens for this elimination reaction they are. And the reason that's true is because there is significant alkene character in the E2 transition state. So we haven't said hardly anything about the E2 transition state. I'm going to just draw an abbreviated molecule. Here's the alpha carbon, here's the beta carbon. Here is the leaving group that is leaving in the E2 transition state with a partial negative charge on the leaving group. Here is the beta proton that is being removed, and here is the nucleophile slash base that is doing the removal. And then here between the alpha and beta carbons is the newly forming pi bond. There's a lot going on in the E2 reaction. The double dagger here just indicates that what I've drawn here is a transition state. There is significant alkene character in the E2 transition state, and that means that what makes an alkene more stable should also make the E2 transition state more stable, lower in energy, and therefore that reaction should be faster. So what I'm telling you is that in the E2 reaction, the more stable alkene forms faster because it passes through a more stable transition state. Does that sort of make sense? Okay. So, as you would imagine, the E2 reaction is not as fast for a secondary alkyl halide, but still okay. And it is slow for a primary alkyl halide, and for a methyl halide, there are no beta protons, so anyway, sorry, that's a commercial from my childhood. You probably have no idea what I'm even talking about there. Go look it up. It's on YouTube. Poor rabbit never got his tricks. Okay, by the way, why would you? Tricks really are for kids. Have you tried them in your adulthood now? Somebody here loves them. Okay, love them. Okay. Question: is it like Skittles or not like Skittles? Are they all the same flavor, or are they different flavors? Who can tell? There's probably a lot of that one ester that tastes like strawberry in Trix. Okay, good. Hey, respect to those of you out there that like Trix. That's fine. Okay. So you can see now some decisions that we can make. If you've got a molecule that's a methyl halide, you don't have to worry about E2. There's no beta protons to remove. If you've got a molecule that's a primary alkyl halide, it's going to turn out that here SN2 is going to beat E2 for the most part. We'll come back to that a little bit. It's a little bit nuanced. If you have a secondary alkyl halide, you're going to be worried about the competition between SN2 and E2. And if you have a tertiary alkyl halide, you're not going to be worried about SN2 at all. Yes?
For the primary carbon, in the textbook it said that SN1 reactions don't happen for the primary carbon in the methyl group.
Right.
Is that the same for E2, or we do see like primary carbons have like just a slow reaction?
No, you can. So your textbook talks about the SN1 reaction, and I'm deliberately delaying on that because we're going to get to that next time. It's true that actually SN1 reactions don't happen for methyl and primary halides. It's not for the same reason as the E2 reaction. It has to do with the fact that the carbocation intermediate that you would get from these two, methyl and primary, is too unstable to form. But yeah, we're going to get there.
So E2 does happen for
E2 can happen for a primary alkyl halide, but whether or not it does happen is going to depend on a second consideration, which is the nucleophile. We haven't done that yet. We're gonna. Okay? So for some of these, we're not yet at a position where we don't have all the information yet to make a decision. Is it E2 or SN2? We've got only part of the picture here, which is the structure of the alkyl halide. We need to now introduce the impact of the nucleophile so that we can make a good decision. But other questions before we do that? Okay, let's talk about, as I said, both of these reactions have the nucleophile / base in the rate law. So you would expect the structure of the nucleophile to influence things, the rates of both of these reactions. And indeed, that's what we see. In general, SN2 reactions is favored by a good nucleophile. Like, thanks for that. I probably could have figured that one out on my own. And an E2 reaction is favored by a good base. All right, well, same to you, buddy. These are great ideas, but how do I know whether a nucleophile is a good nucleophile versus a good base? So there's some general principles, and thankfully, they rely mostly on your pKa intuition, which is why we spent so much time in Chapter 2 on that. Understand that you're going to have molecules that are good nucleophiles and good bases, meaning they aren't too particular as to whether they attack carbon or hydrogen. You're going to have molecules that are good bases but not good nucleophiles, meaning they're particular for attacking hydrogen. You're going to have molecules that are good nucleophiles but not good bases, meaning they're particular for attacking carbon. And then you're going to have molecules that are neither, that are not good bases nor good nucleophiles. And in a lot of cases, this tracks with pKa. So, good nucleophiles are good at attacking the alpha carbon, so they can do substitution chemistry. Generally, good nucleophiles have conjugate acids, there's that term again, conjugate acids with pKa's that are greater than 0. I'm going to put an asterisk on that because there are a handful of good nucleophiles that whose conjugate acids have pKa's less than 0. But in general, that's a decent rule. So what would be on this list? Things, good nucleophiles whose conjugate acids have pKa's greater than 0. Acetate, or any carboxylate anion, is the conjugate base of an acid. So I'm not going to draw the conjugate acid, but you can imagine it. Conjugate acid pKa equals 4. Thiolate, or a negatively charged sulfur molecule, has a conjugate acid, the thiol, whose pKa is around 8. Can I trust you with your notes here that you understand that these pKa's are refer to the conjugate acid and not the base that I've drawn? We're all, okay, good. Another one that you maybe haven't encountered before is azide. Azide has an interesting Lewis structure that's not necessarily important. 3 nitrogens. It has a conjugate acid which you've maybe never seen before, so I will draw that for you. Its pKa is around 9. Cn minus is cyanide is another good nucleophile. Its conjugate acid is HCN. Smells like almonds, and if you can smell it, you might be dead. So when working with Cn minus under acidic conditions, you have to be really, really careful. But anyway, Cn minus is a good nucleophile. There are others with, that we could continue on. So, for example, amino groups. RNH2 has a conjugate acid with a pKa of 11. So that falls into our category of good nucleophile. And then there are others. For example, OH minus, hydroxide, conjugate acid has a pKa of 16. Some alkoxide, like ethoxide or methoxide, so we'll just put a CH3O minus. Conjugate acid, again, pKa of 16, that's a good nucleophile. Another one that you may not have encountered before is something called acetylide. This is the conjugate base of an alkyne whose pKa equals 25. This is also a good nucleophile. Okay, basically anything whose pKa of conjugate acid is greater than 0. Now I'm going to add an asterisk here because I minus and Br minus and Cl minus can also be nucleophiles. That's not so important in chapters 7 and 8. because we're dealing with them as leaving groups. But we're going to see later on in Chapter 9 that we can use them as nucleophiles. So just keep that in the back of your mind that those halides can be good nucleophiles. What do a lot of these have in common? Most of them have negative charges, though the amines are neutral and are still good nucleophiles. Okay, so yes. Should you memorize them? Well, you'll have a pKa table. I can't guarantee that all of them will be on the pKa table, so probably through, I don't know that you'll need to memorize so much as like do a lot of practice so that you just get a lot of experience. Probably the ones that are least familiar to you and are these two new ones, maybe N3 minus and Cn minus that we talked about. And maybe those are worth, if you're going to memorize anything, maybe that's worth it just because they're unfamiliar. Now, what makes a good base? So a good base attacks the beta proton and does elimination chemistry. Good bases generally have conjugate acids with pKa's greater than or equal to 16. Now you see the problem, because all of these things that have pKa's greater than 16 are going to be good bases. So some things are going to be both good nucleophiles and good bases. Others are going to be just good nucleophiles, right? So all of these here with conjugate acids with pKa's lower than 16 are going to be good nucleophiles, but poor bases. All right. Let's talk about things that don't qualify as, let's see, I suppose I can use the word poor instead of not good. Poor nucleophiles / poor bases. These would be things whose conjugate acids have pKa's less than 0. That's a less than sign, yeah. So on this list is just a few things, but we'll put, but not the halides. So water and alcohols in general have conjugate acids with pKa's that are like -2. All right, so water is a poor nucleophile, a poor base. Alcohol is a poor nucleophile and a poor base. So let's see, we've dealt with things that are both good nucleophiles and good bases. That's here. We've dealt with things that are just good nucleophiles and not good bases. Understand, you're going to have to go back and separate this list because I've just shown you all the good nucleophiles together without distinguishing whether they're good bases or not. Here, I've just given you things that are good bases without distinguishing whether they're good nucleophiles or not. I want to introduce, lastly, a category of molecules that are strangely poor nucleophiles, but nevertheless still good bases. And this category doesn't seem like it should exist, because if a good base has a pKa of its conjugate acid greater than 16, that would automatically seem to put it in the category of a good nucleophile. All right? But there is a possibility here for something to be a good base but not a good nucleophile. And this really has to do with sterics. Notice that a proton is smaller than a carbon. It is easier to attack a proton. It is easier to get close to a proton than it is to attack a carbon. And therefore, if you choose a base that is already bulky and already has a hard time getting close to things, it should more readily attack hydrogen than carbon. And so we have some molecules in organic chemistry that we're going to call sterically bulky or hindered bases. They are so big that they can't get to carbon, but they're okay to attack hydrogen. So they're sort of exceptions to our rule. They are going to be reactive enough that you would think they should be able to attack carbon, but they can't because they're so big. One of these is an alkoxide base. It usually comes with the counterion potassium, potassium tert butoxide. Sometimes this is called TBUOK. Sounds like I don't know. Tert butoxide, potassium tert butoxide is how you'd say it. It's the conjugate base of tert butanol, and that actually has a pKa of around 19. So this is more basic than you would expect for an alkoxide. Nevertheless, it's not good at attacking carbon because the bulky CH3 groups get in the way. Okay? So not a good base because, not a good nucleophile because it's so big. There are others that are described in your text that I won't draw here. They have abbreviations DBU and DBN. I'm not drawing them because I don't actually know them off the top of my head. You can look them up in the text. They're sterically bulky. By virtue of the fact that I haven't drawn them here, I'm avoiding the question, do you want us to memorize those structures? No, I don't. But if you see the structure drawn or see the acronym written as a reagent, I need you to recognize that these are sterically bulky bases that are too hindered to be good nucleophiles. All right? Okay, so you got 4 categories of nucleophile/bases. First is a category that's good at both. Second, a category that's good only at being a nucleophile. Third, a category that's good only at being a base. And fourth, a category that's neither a good nucleophile nor a good base. So with that in mind, we're now sort of prepared to do to make some interesting decisions with various reactions and predicting outcomes. So here is an alkyl halide, and here is a nucleophile, and we're going to predict what happens. So start with the alkyl halide. What kind of alkyl halide is that? Is it methyl, primary, secondary, tertiary? Primary alkyl halide. And you know from that SN2 is fast and E2 is slow. Second, let's look at CN-. What kind of a nucleophile/base is this? Let's scroll up to where we were. It's going to check the box for good nucleophile, but how about for good base? No, conjugate acid's pKa is too low to be a good base. So this is going to be in our category of things that are good nucleophiles, but poor bases. That combination, that it's a primary alkyl halide and a good nucleophile that's a poor base, is going to allow us to say SN2 only and no E2. So you would simply do the substitution reaction here, and you would draw that as the SN2 product. Okay? All right. I think that's probably, fine, 30 seconds. All we have time for today. So I will see you Friday. Have a good Wednesday.